Welcome back. So, in this lecture, we would talk about another variety of sensors which belong to the class of variable inductance. So, till now, we have seen capacitive and resistive sensors. They formed one of the classes of these sensors which actually work on the principle of change in capacitance and change in the resistance, which could be in different ways like strain gauge. It was like simple pot, which is potentiometer, and in capacitive, which was very simpler, in which the capacitance changes by changing the distance between the plates or by changing the dielectric medium. So, like similar to this one, similar physical principles can be used in terms of changing the inductance of the coil or the reluctance and the production of eddy currents. This could be also used as the principle for the measurement of various physical quantities like position and velocity. Now, moving ahead, magnetic sensor types, we put them as broader classification rather than inductive type because we have the phenomenon of actually production of magnetic field in the coils. So that is the basic or the common phenomenon between the types of magnetic sensors that we have. So we have variable self-inductance, variable mutual inductance. These are all types of sensors. We have the popular LVDT, which is the linear variable differential transformer. We have the variable reluctance transducer, and we have the eddy current sensor. So all five of them actually, three of them belong to variable inductance, and then two of them are variable reluctance and eddy current, but all of them have the magnetic properties, or the magnetic field is created in all these five. So we classify them into magnetic sensors. So these are the physical principles that are associated with all the five sensors here. Now coming to inductive sensors, so inductive sensors actually work on the principle of actually changing the inductance of the coil. Now if you see from this equation, so we know that the inductance of a coil actually is proportional to n square mu a by L, where for a coil, if you see, n is the number of turns in a coil and mu is the permeability of the core that is present inside the coil, or that is put it inside the coil, or you can say in the concentric area of the coil. A is the area of cross section of the coil, so it could be a smaller area of cross section or a bigger area of cross section. It's not of the coil, it's not of the wire, but it's of the coil that is produced out of this, this coil. You can see one of them below, or two of the coils which is having less inductance and more inductance based on, you can say, different length or different area. And then small l is the total length of the inductor. So which means that we can change the inductance of the coil by changing the number of turns, by changing the area of cross section, or by changing the length of the coil. So which are geometric parameters and which are sometimes difficult, but what we popularly do is actually we change the permeability of the core, because of which actually the inductance change, and that change can be corresponded to the measurement variable, or the measurand, or the physical parameter that is to be measured. Now what happens is, as we put on the alternating current between the two ends of the conductor, it's magnetic flux, or the magnetic this is magnetized, and then we have from the Faraday's law, a magnetic field is produced, and then it's in the form of magnetic flux. So it forms a closed path that extends even outside the coil. So now sometimes we use iron or other good materials are used actually as core, which get magnetized due to this magnetic field, and they itself kind of form the kind of increase the inductance of the coil altogether. So obviously if we use air has the less permeability, so in general without a core, air could be there, but as we move on, as we increase the as we change the type of material that is used in the core, for example we use iron or any other ferromagnetic substance, so we would see an increase in the inductance of the coil. So this is how it looks like. So we have a conducting plate that comes near to this sensor, and then as it moves, it decreases the air gap between the sensor and the conducting plate, as the conducting plate moves, so we can measure the displacement of this conductive sensor. What happens is, as it moves near to the sensor, we have change in the inductance of the coil. We can say the magnetic flux changes because of kind of change in the type of the core, because we're using a conducting material, you can say ferromagnetic material, putting it near to this, so it changes the magnetic flux. We have something called as primary or secondary, or you can say pickup coil, and the main main supply coil. So we can measure those changes in those coils, and that can be corresponded to the displacement of the measurement, or you can say we can use it for position measurement also. Now, the first one is variable self-inductance, where we use a single kind of an E-shaped ferromagnetic body. It's excited with an alternating voltage or an AC, and then the displacement can be measured by putting a ferromagnetic plate again in close proximity. Now, this is the ferromagnetic plate here also. Now, this can be connected to the you can say the object whose displacement we want to actually measure. So as the object moves up and down in this case, so we have again the flux on the magnetic flux that's caused because of the alternating current in this coil. So that changes as per the displacement, and those changes can actually be read out, and then we can actually measure those changes. And it can be useful for us to measure the displacement and also the frequency with which we can calculate the velocity of this object also. Now, in this one, we have again a similar one where we have, rather than E, we can have again a simple U shape or something like that, where we have a coil. Again, it's excited by an alternating current, creates a magnetic field. Then we have again an armature, or you can say a ferromagnetic material that goes up and down based on the object that it's connected to. And then there's a reduction in the air gaps, and accordingly it changes the inductance, that is the L is changed, increased or decreased. And if we see from the basic Ohm's law, the current flowing in the winding can be given by, for an inductive kind of a load, we have I is equal to V by omega L. You must be aware of the basic definition. I V is equal to L di by dt. Also, this the voltage across the inductor is given by this type of function. Similarly, we can say that V it can be given as I is equal to V by omega L. Now, for fixed value of omega and the voltage across the inductor, the equation can be written as I is equal to 1 by K, where K is some constant. So it means that the current is inversely proportional to the inductance of the coil. Now, this relationship of inductance actually bears a relationship with the displacement. So we know that the inductance of a coil can change if we change the motion of the ferromagnetic material. This is a ferromagnetic material here. So if we make it move up and down, it will cause decrease or increase in the air gaps, and then accordingly it will cause change in the inductance, because that is closely related to the type of core that we are using, or the type of material that we are using in terms of core. So, but that bears a non-linear relationship between the displacement and the conductance, in the inductance of the coil. So as we change D, the KL changes, so accordingly the current through the inductor also would change. So this can be calibrated, the current can be calibrated, you can say correlated with the displacement to be measured, and then we can actually use this as a position sensor. In the variable mutual inductance, we have a similar principle, but here we use the concept of mutual inductance, in which, again, according to Faraday's law, we have change in magnetic flux in a coil of a wire will induce a voltage in the nearby coil. So this is the secondary circuit. This is the primary one, where we have excitation. It creates a magnetic field, and we have another secondary circuit. Because of the changing magnetic field, we have induction in the coil. So the magnetic field will induce a current in this coil, which we can actually measure. But again, this would depend on the core that is kept in between, so which increases the flux. So we can use this, again, a similar principle, to measure the displacement and the frequency, where we can change the ferromagnetic material and make it move up and down. Accordingly, the amount of flux that will move through this core will actually change, and accordingly it will change the production of current in this circuit, which can be easily tapped. All right, so that can be again corresponded to the displacement of the object that's to be measured. So these are the variable, you can say self-inductance and the mutual inductance principles, that are the variable inductance principles that are used in the, considerably, you can say, that are used so popularly in the industry. So the application could be even to measure the profiles, or you can say to measure the profile of the, of some objects. For example, if you see here in terms of it's sensing a rotating object, so it's like a cam where you have a bulge here. So what it does is, so because of this cam or because of this eccentricity here, as it moves near to the sensor, so it will have lesser displacement between, or a lesser distance between the probe and the cam, this part. So there will be change in the current. So accordingly we'll see a displacement like this, or you can see a profile like this, which can even tell us about the profile of the object that's to be actually measured. So in a kind of a profile measurement device, or it could be even like this, where we have on the inclined surface. So this inclination can be attributed to this type of change in the current. And similarly, we can have an axial approach, where we go from, let's say, we make the inductor go up and down, or sensor go up and down, or we can make the object go up and down. Accordingly, we'll have change in the current that is produced in the secondary one. All right, so this is the picture of the real inductors that are used in the industries, and they have considerable applications in the, obviously, position measurement, position sensing, or you can say even in the detection of some objects, because we can detect an object is nearby, or an object has been placed away. Because if we keep an object away from the inductor, obviously there will be changes than keeping it closer. So again, this is similar example of an inductor coil, which is shown here. So where you have an input, kind of the input coil, which is energized by an alternating current, and then you have a secondary in which the current is induced due to the change in the due to obviously the magnetic field created by this, but that can be changed by making this core move up and down. So accordingly we can see change in the voltage of this coil, or accordingly the current. One example that I was interested in showing you is similar to what we have seen in your dynamics lab, if you have really noticed carefully. So this setup that we use in the dynamics lab, this is from Gunt, and this is more of a universal vibration apparatus, where you would like to measure the correlate the vibrations of a single link subjected to spring and damping effects, and then maybe eccentric mass loading and all those things. In order to measure the displacement of this this beam that is placed here, this setup is available in our dynamics lab. So in order to measure this, where there is a spring of constant K, there is a damping of damping coefficient C, for example, and there is some loading, extra loading here, and then there is a hinge. So we load it with some kind of, we can excite it also, or we can make it move kind of a free kind of a movement. But in all these cases we have an inductor placed here. So this is the sensor that is placed here. So we have a profile meter also, which takes the profile, but we have a sensor here, which is the inductor, or you can say inductive sensor. So this is another application. We want to measure the profile. So you must have done this experiments, and you must recall that we would get some profile like this for this inductor also. All right, and for smaller, we would get obviously the different profile, and sometimes we would get even high frequency. So all this would correspond to the displacement of the beam at this end, and we could correspond it to basically we could find the frequency of this kind of output, and then accordingly that could be correlated with the frequency of the beam which it is supposed to move, the natural frequency or the damped frequency. So this is another application of this type of sensor that we generally use in our labs. I just wanted to make it kind of give it some practical significance of inductors. Obviously the advantages are it ignores water oil, dirt, and non-metallic particles. It is insensitive to target color or target surface finish. It's resistant to dirt, short circuit protected, and it withstands high shock and vibration environment. This is one of the good advantage, or you can say good things about inductive sensors. Some of the good things about inductive sensors. And similarly, it has limitations that it can only detect metallic objects, because obviously if you have plastic, it doesn't really matter whether we move it near to the inductor or away from the inductor, because it doesn't allow the magnetic field to be to pass through it. So obviously it doesn't really affect the permeability of the core, and obviously it doesn't increase or decrease the inductance. So obviously using plastics would actually doesn't really change the inductance, and hence if we want to detect the movement of the plastic objects, which it will be difficult. So this is kind of a limitation for these type of sensors. But if you have different materials, different inductive properties, so obviously you will have change in the sensing distance between different objects, because they will have different effects on the inductance of the coil. So for example, steel, it has the longest sensing distance, while non-ferrous materials like aluminum or copper, it has much shorter sensing distances. So we may use even non-ferrous materials here, but they would have much shorter sensing distances. So in general, they are well suited to shorter range applications, as the inductive effect wears off with growing distance between the sensor and the object to be detected. So obviously, inductive sensor, one of the limitations you have to keep in mind is that they are used for shorter range applications. This is one important thing. And then second thing is it's used only with ferromagnetic materials, or you can say it's used to with metallic objects which have inductive properties. We may use non-ferrous also, but it should have some inductive properties. That is very important. What we could do is sometimes we have, even if we have plastic objects, so what we could do is we could add some metallic objects at their ends, and those metallic objects can be used to sense the distance, and then the rest of the movement of the plastic object can be also tapped. But that is kind of adding it, additionally making it cumbersome, but that can be taken as a solution to the problems if we have inductive sensors only to be used. Similarly, we have LVDT, which is linear variable differential transformer. So as the concept is similar to the concept of mutual inductance. So where we have a primary coil, which is input voltage here, we have a primary coil, and then we have the secondary coil, but that secondary coil is formed in a circuit line like this. So this is how it looks like in terms of a cross section. So we have primary and secondary, and then we have a core which is placed in between. So this is displaced front and back, for example, in this case. So the displacement of this core actually would cause change in the output voltage, because obviously variation in the magnetic flux and obviously in the mutual inductance between the input and the output. So obviously this can be corresponded again to the displacement of the measurand. So this is where we use LVDTs. These are very common or very popularly used. They have really good advantage in terms of life. They have really we can use them for longer durations without wear, and they are highly accurate as instruments. Now we have variable reluctance sensors. So in this case, a coil is wound on a permanent magnet rather than on an iron core, as we have seen in the variable inductance sensors. So if you see this thing, so there's a coil here that is wound on a permanent magnet. So in this case, we don't have an iron core, rather we have a permanent magnet on which a coil is actually wound. And then we use some kind of an arrangement. For example, this is particularly used in the ABS sensor or in some other applications also. So what happens is actually because of the change, or can say the magnet in the sensor actually, which is placed here as the permanent magnet, it creates some magnetic field. So as you move a ferrous object like this, for example, we have a tooth rotor, the distance between the probe and the tooth actually is somewhat, let's say d, but the moment the tooth moves ahead, then we have this gap, so the distance increases. So as the distance increases, obviously it is kind of giving us, it would give us kind of a a signal which is not appreciable, for example, but in this case you may have a good amount of signal. So this change in signal would be something like this that we will get as an output. So what actually happens in variable reluctance sensors is that rather than using a coil which is energized by an AC signal, we rather actually look at it in a different principle, whereby a permanent magnet which creates a magnetic field actually around it is disturbed by this motion of the kind of a an object, ferrous object, which is closed, which is placed nearby to it. So the moment we put it near to it, so obviously it changes the magnetic field, and it causes the changing magnetic field causes production of the voltage, or you can say current, in the coil, which can be picked up. And the moment it goes to the far away part, so obviously the voltage drops, and that voltage drop can be corresponded to this point, and the tooth part can be corresponded to this one. So all this can be picked up, and then we can take it to a signal conditioning circuit. We can get this type of profile, which actually the frequency would tell us the velocity of this tooth type of a profile. So obviously I have written the principle here as ferrous object moves by the sensor. A change in the magnetic flux induces EMF in the pickup coil. So this is known as the pickup coil. This coil here is the pickup coil. So in this case we use a ferromagnetic gear wheel, which is in this form. So in general, in the variable reluctance ones, we have one important thing that we have to remember is that we have a magnet inside the coil rather than an iron core, and that magnet creates a magnetic flux around it, or a magnetic field around it. And because of this type of arrangement, a tooth type of a gear arrangement, which causes the distance between the sensor or the probe and the tooth to change because of the profile of the tooth gear, or you can say target gear here. So this air gap obviously here would change, and accordingly it would cause change in the magnetic flux, which will induce an EMF inside the coil, and which can be picked up. So this is the principle that is actually used in the variable reluctance sensors. So the output obviously is a sequence of positive and negative pulses that we have seen, which is evident here, whose frequency actually is proportional to the rotational velocity of the gear wheel. The applications are shaft velocity sensor for ABS. In the anti-lock brake systems, we use this as the shaft velocity sensor. We have in traction control. So this is how it looks like in ABS. So you have ABS reluctor. We call it a reluctor ring. It seems to be as a gear, but it's more of a part of the sensor also now, because it's called as a reluctor ring. And then we have a wheel speed sensor that is more of this type of arrangement only, which we call as variable reluctance sensor. Obviously it detects this type of profile, and this goes to the electronic unit. So we have a profile like this that comes out of this type of sensor. So obviously we can use it for crank and camshaft position sensors also. So even it can be used in the detection of some cracks or the missing parts in the gear. For example, you have a 32 teeth gear that is placed here, and we want to actually put it and then check it for cracks, or check it for the damaged portions, or check it for the missing teeth. So in the normal sense, we may get something like this. If it's a normal teeth, everything is fine. There are cracks, so we may get some output like this. If it's damaged, we may get something like this, a longer duration at some instances. If it's a missing one, we may get something like this as an output in the profile, obviously in the oscilloscope, or maybe you can get it in other type of measuring electronic measuring signal measuring instruments. Fine. So this is how we may get as a profiles, and this can be even converted to digital forms also, where you have a longer time period, which actually tells you about the correspondence with this type of output. The limitations are, again, the EMF is proportional to rate of change of magnetic flux. So which means ferromagnetic materials or ferrous materials must be moving for sensor to generate signal. This is very important for this type of, we cannot obviously have plastics and others in this case. It's difficult also to mount any ferromagnetic, or you can say ferrous materials on this type of sensor, because you need to put it on every teeth. Then the output voltage is actually dependent on the velocity of the tooth field, so it may reduce the performance at slow speeds. In this case, we really require conditioning circuitry to yield a useful signal, because the moment we have an output, this output type of output may be actually very small. Small in a sense means a very low voltage also, so which needs to be amplified and you can say filtered These two are very important, and obviously it all leads to signal conditioning circuitry. So this type of sensor actually would require the conditioning circuitry to yield a useful signal. Then we have eddy current sensors. Eddy currents are a different phenomenon actually, whereby we have a coil, if you see here, which is energized by an alternating current, and then if we have some conducting material placed near to it. So because of the high frequency, you can say using an oscillatory high frequency alternating current, what happens is, because there's a magnetic field that's created, but because of high frequency, you can say changing very fast magnetic field, so we have an induction of some currents on this conductive material, which are called as eddy currents, which move in a circular path like this. So these currents which are moving in a circular path like this on the surface of the conducting material will have its own magnetic field. Okay, induced magnetic field again. That magnetic field will actually interfere with the eddy current's magnetic field, and change in this or the interference in this actually is picked up by another coil, which actually corresponds to the displacement of this conductive material. So you can again read from this, because of the high frequency of excitation, eddy currents are induced. So high frequency excitation is important, because then only eddy currents are actually induced in this case. So again, the eddy currents alter the induction of the probe coil, inductance of the probe coil, because they change they try to interfere the magnetic field of this. Obviously that will change the capital L of the probe coil, and this change can be translated to a DC voltage also, that is proportional to the distance between the probe and the target. So it's how it looks like actually in actual sense. So you have the induction coil, where you have alternating current, actually magnetic field produced, and then you have a pickup coil, in which because of this magnetic field there will be current produced in this, or you can say voltage developed in the pickup coil. But because of the eddy currents that are produced and the secondary magnetic field that is produced because of these eddy currents, this changes the magnetic flux, or this kind of it alters the magnetic flux, and because of which there is change in the voltage, or you can say change in the current at the pickup coil. So you will have changes in the pickup coil. So that change can be corresponded to the displacement of this sample, or you can say displacement of this object whose displacement is to be measured. So again, it talks about production of eddy currents. So alternating current feeds a coil. It's fed to the coil, and there is a magnetic field produced. Then an electrically conducting measuring object is placed near to this type of arrangement, which creates eddy current in the form of these concentric circles. And because of these concentric circles, you have because of these currents in the form of concentric circles, you have again a magnetic field produced, which alternates, or which alters the impedance of the coil, or you can say the inductance of the coil. And this can be corresponded to the distance between the sensor and the object whose position is to be measured. Now these are some of the examples, or some of the applications of this type of sensors. So we can measure spindle growth, we can measure the spindle growth, measurement through rubber sheet on roller, measurement of roller gap. So this is where the eddy currents are installed. So obviously the distance between the probe and the object whose distance to be measured changes. So in the engine optimization, you can connect it to the crankshafts. So even the variable reluctance could be used here, but this is a case of an eddy current sensor. So you can have 3 eddy current sensors, and because of crankshaft and concentricity, if it's different, so it can be also measured, it can be picked up. Even the actual movement of the crankshaft can be picked up for optimization or for creating better designs. The lubricating gap can also be measured with these types of sensors. So oil film thickness. The advantage obviously in this case again are contactless. This is with all the type of magnetic sensors we have, all of them are actually contactless sensors. We don't have any contact with the object whose position is to be measured. These are portable. They are sensitive to small cracks and surface defects, and this type of eddy current kind of an arrangement. So measurement resolution is high as 0.1 micrometer, And it can also work with, as you have told, with the other kind of self-inductance or variable inductance case, where we can even target and have a non-conductive target with which we add some aluminum tape, or we can have some other metallic compound added, which whose actually which can be responsible for changing the inductance of the coil, and that can actually help us in even using these plastic materials whose displacement is to be measured. So we can solve that problems with this type of arrangements. So obviously the applications in this case are the material discontinuity. So there's a material discontinuity, change in the eddy currents, and accordingly change in the magnetic flux. This will have a different different kind of a effect on the receiver coils induced current. So obviously we can detect the material discontinuity with this. So this is kind of an application in the gear, where we actually try to measure improve the performance of the gears by having again some eddy current sensors installed and trying to measure the cracks and trying to measure the displacement. Obviously in the crack detection, again this is an arrangement where we want to measure the cracks in the shaft as displacement sensor probe. This is how it looks like in real sense. So obviously the limitations in this case would be the depth of penetration is limited. The surface must be accessible to the